Get started now. So thank you all for joining us in the first tutorial session of the conference. My name is Emily Denton. I'm a research scientist at Google. It's my pleasure to be introducing this tutorial today because it's organized by two colleagues of mine, Margaret Mitchell and Ben Hutchinson. The three of us, plus a few more folks here around the FatStar conference, are all part of a team working on Google, working to ensure the ethical development of AI, a core component of which is machine learning fairness. So more specifically, Ben Hutchinson is a senior engineer at Google, and his interdisciplinary research includes learning from the social sciences to inform the ethical development of AI. Prior to joining Google Research, Ben worked on a variety of Google products, and he now uses this experience to work closely with product teams at Google as a consultant on responsible practices and the development of fair machine learning methods. Ben also has a PhD in natural language processing from the University of Edinburgh. Margaret Mitchell is a senior research scientist at Google, where she co-leads the aforementioned ethical AI team. She also helped draft Google's responsible AI practices, and she's been instrumental in shaping Google's internal fairness and ethics efforts. Prior to joining Google, Margaret worked on an award-winning image captioning system that was subsequently turned into an application for the visually impaired and won the prestigious Helen Keller Award. In the course of this work, Margaret noticed a variety of gender and racial biases in the captions, and she introduced some of the very first work on fairness in vision and language systems. She's written more than 40 papers in computer vision, natural language processing, cognitive science, and AI ethics. She's chaired, organized a variety of workshops on these topics, and she also has a really fantastic TED Talk on the topic of computer bias in vision and NLP, which has received over 1 million views. So please join me in welcoming Margaret Mitchell and Ben Hutchinson.
Thanks, Emily. Everyone can hear me okay? And then also, if I walk over here, can everyone hear me okay? Everything's good? Okay. Oh, nope. All right, let's see. Thusly? Yes. Yeah, okay, that's really loud. All right, great. Cool. So this is now, I have too many microphones. Okay. Thank you for coming to our tutorial. We're going to be covering a lot of ground. There will be more and different ground tomorrow at our talk, which will be given by Ben. And also, please feel free to read the paper. Okay, so a little bit of an introduction. Who we are, what we are, why we're doing this. So, as Emily mentioned, I'm Margaret Mitchell. I often go by Meg, and this is my teammate, Ben Hutchinson. And this work is very much indebted to Shira Mitchell, who kindly checked our math, etc. Neither of us have a statistics background, and so she made this work very legitimate. We really couldn't have done it without her. Cool. So a little bit of a brief history of fairness in ML, basically to get everyone on the same page. There's a sort of idea that in the past 10 years or so, fairness in machine learning is relatively new. The concepts and ideas are relatively new. And there's been an increase in interest in the various fairness issues that come out of ML systems more and more in the past few years. This suggests that the time before something like 2011 might be like the dark ages of ML fairness. But actually, we found that a lot of the ideas and concepts have already been invented and thought of before in a slightly different context. So in the period of the 1960s, 1970s, following Brown versus Board of Education, actually in the 50s, there was a sort of golden age of research into test fairness. Coming out of the 1964 Civil Rights Act, people were trying to think about how do we make sure that we don't discriminate when we give people jobs or when we do standardized tests for schools. How do we make sure that things like gender, color, and race don't yield, fundamentally different opportunities? And we'll see throughout the slides that with the time they look at color a lot. So we'll have some slides that are like black and white, sort of borrowing from the original ideas from the 60s. Cool. So we're in something now like the third reconstruction, and our hope here is to learn a bit from what happened before and bring these old ideas back into light now that there's a renewed interest. Cool. So here's a little bit of the difference between the two time periods. It's important to understand the sort of the different values that individuals working on this had, what their priorities were, in order to understand the biases and skews in their approach to working on fairness, and so see some of our biases and skews in our approaches to working on fairness. So in the 60s and 70s, the focus was on educational testing and job testing, and this came out of the '64 Civil Rights Act, and people were really interested in trying to see how can we really apply these ideas mathematically. In more recent times, the focus has been on surveillance and policing and sentencing, still with some of the very same fundamental ideas of trying to have sort of equal experiences for everyone. The 60s had a focus on standardized tests. This is because it was pretty common for standardized tests to be used as a means to get a job, as a means to get accepted to a school. This is still very common, actually. The SAT is, I think, still used today, unless I've gotten much older, then maybe it's not, but I believe the SAT is still pretty common, and some of the math ideas that were developed for the SAT were developed during this time period. So before further diving into the history of testing fairness, it's useful to briefly consider the structural correspondences between the tests and the ML models. So test items are questions, and they're analogous to model features. Item responses are analogous to specific activations of those features. And scoring a test is typically a simple linear model that produces a sum of scores, possibly weighted. And sometimes test scores are normalized or standardized so that the scores fit some desired range or distribution. And this is similar to neural networks, which similarly produce a score based on a bunch of sort of input features. Because of this correspondence, much of the math that was developed for test fairness is directly comparable. And many of the underlying ideas in earlier fairness work trivially map on to modern day ML fairness. So we take this idea to heart that history may not repeat itself, but it may rhyme, which is this idea that there's probably going to be very, very similar parallels with some slight differences, and it's useful to try and dig into what those exact parallels are. So learning the history helps us to see our current biases and current skews, how we ground on the different kind of concepts that we're interested in. It helps us avoid duplication of effort and to better understand our own current problems. It also helps us learn from others' mistakes. So there was actually a lot of writing after this sort of wave of fairness research in the 60s and 70s, talking about lessons learned and why what was really popular at that time ultimately didn't end up catching on. And we hope that by bringing these sorts of insights into modern day, we can avoid this kind of fate for ML fairness. All right, so this is the end of the introduction, and then we have a few things to cover. We'll be having a quick group exercise, and this is sort of going to be split between me and Ben, so we'll be alternating back and forth. All right, so a bit of context. This is for FAIR machine learning recently. I'm going to be going over some notation and criteria that we're going to use throughout the rest of this talk. Hopefully this gets people more or less in line with what's going on. It'll be a pretty brief review of fairness definitions, and so there's a lot more like reviewing that can be done, but hopefully this is kind of sufficient. Cool. So I'm going to have some basic concepts here. Say that we want to look at some attribute A, which is represented here on the y-axis, and we want it to be independent of some predicted real valued score, which we call R, and that's represented here on the x-axis. This is something that might come from a model or from a test. And we can represent this pretty simply using this notation at the bottom. A is independent of R. This is equivalent to this probability. And some of these things are used sort of interchangeably in the literature. And this entails that there's no correlation between A and R. And that's kind of what this picture is showing. So A is independent of R. Knowing one doesn't help you know the other one. This relationship is important because we'll see that in in earlier work, some of these same ideas were captured, but in the language of correlation as opposed to the language of independence. Another variable we'll be using throughout is the decision, D. This is something that can be created, for example, by choosing a threshold on your scores and saying anything before this is accepted, anything after this is rejected. It can also be based on a bunch of other things, but this is sort of the most simple case. And these basic variables we're going to put up in a corner in order to go through the rest of them. There's one more variable to talk about, y, the target variable to predict. So given some task like predicting GPA, we might plot what the actual GPA is on the y-axis, what we predict the GPA to be on the x-axis, which we'll represent with y hat. And doing that, we can sort of choose another threshold and get a binary classification matrix in order to figure out things like true positives, true negatives. And this also helps us trivially get to a bunch of other fairness definitions, which can be stated in terms of rates for the different errors from the confusion matrix metrics. So say that we wanted to create some situation where the predicted GPA, given the actual GPA, is constant for all subgroups. This is what's essentially equality of opportunity. This is entailed by basically equality of odds, which is the same as saying A is independent of y hat given y. So we're going to try and use really similar notation throughout, but just to kind of let everyone know, these are the basic ways that things are switched around in the literature. Okay, so those are going to be at the top there to help people kind of know where we are with our variables. Right. So let's talk about what these criteria are. So something like A is independent of D or A is independent of R, we might call independence, and this is borrowing from the book from Solon, Moritz, and Arvind. We'll call A is independent of Y given D sufficiency. A is independent of D given Y as separation. This is also known as equalized odds. These are all sort of independence-based criteria. All of these entail different kinds of probability-based criteria, and these also map onto a lot of current fairness definitions. These can be estimated, for example, calculating the expectation, which gives you a similar kind of way of talking about the same fundamental ideas. And we'll call the measures that are grounded on the decision perspective, and the measures that are grounded on the target perspective. So now we're going to switch to a bit of context and go back in time a little bit and walk through previous test fairness work.
Right, so before I get to the historical definitions of test fairness, I think it's useful to briefly cover some of the context in which this work was happening. So following the decision of Brown versus the Board of Education, an increasing desegregation of schools that followed, sometimes by force, we see black and white students in classrooms together in unprecedented numbers. And this period coincided with rapid growth in the use of standardized tests, such as the SAT, which was applied to black and white students alike. Similarly, at the time, in the workplace, standardized tests were being used in the field of industrial psychology. In fact, one survey from 1963 found that 90% of employers surveyed were using selection tests. One such test, known as the General Ability Test number 10, was in fact found in 1964 by the Illinois Fair Employment Practices Commission to be discriminatory. And although this was later overruled by the Illinois Supreme Court, this case was covered in the national press and got a huge amount of attention. It got a huge amount of attention in Washington as well, where it actually influenced the writing of the Civil Rights Act of 1964. So that act specifically made it illegal to discriminate both in the domains of education and employment on the basis of race, color, religion, sex, or national origin. And immediately after the passing of the act, we see discussion among academics of what the implications are for testing. What are the implications for people developing tests, for people using tests, for people making decisions based on tests, for employers, and for educators? It was recognized, for example, that tests, questions, may require cultural knowledge. So if you saw these questions at the beginning, these are from a test that was given to students in 1964. And regarding such tests, Anastasio wrote that it's impossible to devise a test that is free of cultural influences, and the most we can hope for is a test which only presupposes experiences that are common to different cultures. Nevertheless, there was optimism in some quarters that indeed fair tests could be devised. Robert Guion felt at the time that if we could do so, then barriers to economic opportunity would fall down. Writing of the period, he said that many testers jumped to an immediate and often irrational defense of testing, and many critics of testing began to regard the employment test as the clever subterfuge of confirmed racists. And so I think we see parallels here as well with machine learning. So as the 1960s drew to a close, with the use of standardized tests continuing to grow, we see the start of a series of calls for moratoriums on standardized testing. The figure on the left here is Charles Thomas. He was the founding president of the Association of Black Psychologists, and he led the first of these calls. And of course, the 1970s kicked off with Griggs versus Duke Power, in which the US Supreme Court prohibited practices with disparate impact unless there is a demonstrable relationship to the job. So with that historical context in mind, I'm now going to turn to look at some of the quantitative definitions of fairness that arose in the 1960s and 1970s. And what we're going to see are these remarkable similarities between test fairness of the 60s and 70s and contemporary machine learning fairness. We're going to see lots of competing definitions. We're going to see proofs of incompatibility between those definitions and many other parallels. And the first parallel to point out, as Emma alluded to earlier, is between the variables used to represent testing and machine learning. So in both cases, we're trying to make a decision on the basis of the prediction of a target variable. Just now we have a test score rather than a model score, and that test score is calculated based on test responses. I'm going to use a running example through part of this talk based on law school admissions. So the decision we'll be considering is whether to admit someone to law school. And to do that, we'll be predicting their first year law school GPA grade on the basis of the law SAT test. And at this point, you might even be wondering, well, why is prediction of GPA something that we should make decisions based on? And I'll come back to that later. So these graphs just summarize some of the distributions of data in the law school data set. We'll just be looking at three variables: race, the LSAT score, and the GPA score. And just two things to point out here is that the white group gets higher scores both on GPA and SAT on average. And the other thing to point out is that the correlations differ. For the white group, there's a correlation of 0.24 between LSAT and GPA, whereas for the black group, the correlation is almost zero. So the first definition of fairness we're going to look at today is due to Richard Darlington in 1971. He was a psychologist at Cornell, and he was interested in understanding the long-term effects of early childhood education, and as well as critiquing claims about race and intelligence. And the question he posed was whether the fairness of the LSAT score, so that whether the fairness of that test could be determined simply by looking at a various set of correlations, specifically the correlation between race and GPA, the correlation between SAT and GPA, and the correlation between race and SAT. And so the question is there a function of these three correlations that will tell us whether a test is fair? And he has this, I think it was rather philosophical paper, because rather than just like arguing for one approach, he actually looks at a range of different definitions and considers them all. And the reason he does this is because by the time of 1971, there were already a lot of competing definitions out there, and they were phrased in different frameworks. So he was trying to frame them all in the common language of correlation in order to be able to compare them directly. So the first answer he considers to the question of what a fair relationship is between race and test score was motivated by similar to concerns to what today we might call sufficiency. That is that the independence of race with a target variable conditioned on the test score. Right, so we have independence of race with the target variable conditioned on the test score. Except instead of phrasing this in terms of independent, he phrased it in terms of this partial correlation, which is a slightly different thing. So in the special case when A, Y, and R are all multivariate normal, this actually implies the correlation condition that Darlington has. And he constructs what I think is this rather clever graph to illustrate the relationship. This graph has a lot in it, so I'm going to step through it. So the x-axis down here is a correlation. It's the correlation between GPA and SAT. The y-axis is the correlation between race and SAT. And what he's plotted here is the fair values. So the fair values of this correlation with respect to this correlation. And this whole graph here is assuming that we have the correlation between race and GPA that we observe in the law school data of about 0.32. And so a couple of things to point out. If the correlation between GPA and SAT is also 0.32, then in order to be fair by this definition, we actually need a perfect correlation between race and SAT. If, on the other hand, the correlation between GPA and SAT is 1, that is, if the SAT test is a perfect predictor of GPA, in that case, the fair correlation between race and LSAT decreases to just 0.32. And the nice thing is you can kind of look at this for any range of values in between. So the second answer that he considers to this question of what a fair correlation is motivated by the consideration that maybe we should aim to select a proportion of people from each group as are qualified within that group. For example, suppose we select 50% of one group who are qualified and 50% from the other. So the way he expresses this is that the correlation between race and the test score should be equal to the correlation between race and the thing that we're trying to predict. And so when he graphs this, because this graph is just for the same value of correlation with race and GPA, we get this flat line here. And one nice aspect of his method of graphing and visualizing this is it lets us look at the conditions under which both fairness conditions can be satisfied. So in this case, they can only both be satisfied if we have a perfect correlation between GPA and SAT. Darlington's third definition is motivated by today what we might call separation or equalized odds. That is the conditional independence of the independence of A and R conditioned on Y. Although again, he expresses it in terms of the partial correlation. And similar to before, this is related to this independence expression, but it's only entailed by this in the special case when A, Y, and R are multivariate normal. And again, plotting this, we again see that they only agree with each other when we have perfect correlation of the test and the GPA. The fourth definition he looks at is related to what we might call demographic parity. Again, instead of independence, he phrased it in terms of correlation. And in this case, in fact, this is just implied by this independence expression. So to summarize, we have these four definitions of fairness. Here I've added in this point showing where the law school data set fits, given the observed correlations in our data. So we see it doesn't meet any of the conditions, but it's kind of halfway in between definitions 1 and 2. So one really nice aspect of this visualization, I think, is it lets you directly see the incompatibilities. And so we just see this point here. So if the test is a perfect predictor of GPA, then we see that some of the definitions are compatible. Or if the test has 0 prediction of GPA, that is, if the test is useless, again, these two agree with each other. And the third condition is if this correlation up here is equal to 0, in which case this horizontal line just moves down and becomes equal to the bottom line. So if Darlington is interested in how can we tell if an existing test is fair, but he's also interested in informing people who are constructing tests. And he says, well, their goal should be to maximize the correlation between test score and GPA, such that one of these 4 fairness definitions hold. So this is the original goal that he considers. And he actually, in his paper, discards this goal in favor of a different goal completely. In his opinion, like a crucial motivation of fairness is to help disadvantaged groups. And he thinks the degree to which we want to help disadvantaged groups is a policy decision. And so the approach that he actually advocates for is to have this kind of K constant, which is chosen through an explicit policy decision. And then we try and maximize the correlation of the test score with a weighted combination of race and the target variable. So this is these are the fairness criteria that M presented earlier. And now we can add a 4th column, which is these correlation-based criteria. And we can see again that some are in those kind of decision and target perspective rows. And then his 4th, or it's actually his 2nd criterion, forms a new category down at the bottom there. So what takeaways should we have from Darlington's work? Well, I think this kind of clever geometric plotting of the criteria shows that there's room for kind of interpolating between them as well. That is, if we have different ideas about fairness, we can actually consider an entire spectrum of interpolations. Another thing I like about this graph is it lets us show that as the model accuracy decreases, as we go from right to left here, we get increasing divergence between these kind of separation and sufficiency requirements. So Darlington's first criterion was actually motivated by some prior work by Tian Cleary. Tian Cleary worked both developing tests and as a professor studying fairness in tests for several decades. And she was interested in the question of using test scores to try to predict the target variable. So whereas Darlington was interested in the fairness of the test scores, she was interested in the fairness of the predictions made using those scores. And so her approach was to train a linear regression model using the SAT and the GPA, and then she would say that a test is unfair for one group if it tends to underpredict the GPA for that group. And this idea is actually closely related to what we call sufficiency or independence of A with Y given R, because the idea is that if a test works equally well for all groups, then knowing which group someone is in shouldn't help you to predict their GPA score. And thus it also connects with Darlington's definition. One, which was his attempt to reformulate her definition. So what can we take away from this? Well, I think that in regression tasks, looking at the average difference between the predicted and expected value of the target variable can be an informative measure of fairness. So around the same time as Cleary, and influenced by her work, was James Kirkpatrick. He worked in industrial psychology. He wrote what is perhaps the first book on testing and quantitative fairness in testing, which is Testing and Fair Employment of 1968. And his goal was to predict job performance accurately, even when a test itself might be known to be biased. So to do this, to accurately predict job performance, he proposes to actually use race explicitly in the regression equation that's being used to predict the target variable. Note this assumes that you know the race variable at the time that you're doing this. And this use of the race variable A when predicting Y has some parallels in machine learning as well. Both Hart and Dwork have different approaches which use A in different ways. Hart has the derived predictor, and Dwork has the notion of a decoupled classifier. So we saw that Denton cared about the fairness of scores, Cleary and Kirkpatrick cared about the fairness of predictions, and then we see a bunch of other researchers of the period looking at the fairness of the decisions that are made using those predictions. And so as Em pointed out, we can look at this two-dimensional space, this plotting of LSAT versus GPA, and divide this into 4 quadrants. And 2 of the researchers in 1973 who took this approach, Robert Lynn, first had the idea that we might look at having equal precision or equal positive predictive value, same names for the, or different names for the same thing. Whereas Nancy Cole proposed using equality of the true positive rates. Then in 1976, Peterson and Novick said, hey, maybe we should care about true negative rates as well, and care about equality of true positives and true negatives at the same time. And so this is directly equivalent to the independence of A with D given Y. Although they dismissed the likelihood of this happening as very unlikely. And similarly, they look at the requirement of having both equal negative predictive value and equal positive predictive value, what today we might call sufficiency. And again, they dismiss this as unlikely. So another researcher who was looking at the fairness of decisions took a slightly different approach. And so this is another one of the researchers who inspired Richard Darlington. And Robert Thorndike, his idea was to select an equal proportion of people from each group as are qualified from each group. It's kind of hard to get your head around that at first, so I think maybe the math might be easier here. His idea is that the rate of deciding to select someone to the rate of them having a true value for the target variable, that this ratio should be constant for all groups. And this doesn't really have a direct parallel in the machine learning literature, although Cotter last year has pointed out that sometimes in machine learning, not necessarily for fairness reasons, but you may want to have a system to make a policy decision to achieve something like this, which is very similar, just replacing, this is a kind of a special case of Thorndike's constraint, where it's equal to 1. So this slide is just summarizing the researchers from the historical period that we've mentioned today and that we discussed in the paper as well. And you really see this kind of crescendo into the late 60s and mid 70s, and then it drops off again. And in the paper, we go through more detail about all the correspondences between quantitative definitions in testing and in machine learning. As well as these parallels, we do see some differences, of course. We see different domains of application. In testing, we also see more consideration of regression problems and more focus on the fairness of scores, I would say. I would say machine learning, in contrast, has had more focus on classification and the fairness of decisions. So our takeaway from this is that history hasn't repeated itself, but it has rhymed. So we're going to stop here for any questions about the first half.
And we have a microphone if anyone has a question.
Sorry, just a quick, easy one. What happened in testing after 79? Did it was it all solved and it just?
Part
Oh,
two.
that's part 2.
Coming
Sorry.
soon. Sorry, that's part 2. We'll get to that soon.
Hello. Was there any research on involving people who are being discriminated against in the design of these tests?
That's a great question. And I should say that the field of fairness of tests is actually an enormous field, and it covers all sorts of problems and interesting questions. In this talk, we're looking specifically at the quantitative definitions, but there's been like a huge, we're really covering like a tiny part of this field.
I just wanted to make sure I understood what the word qualified meant, like throughout the past couple of slides, because it wasn't quite clear to me.
Oh, qualified?
Because does qualified just mean above a threshold, or does it mean that there's like you turn some score into a here and then in like a couple of slides previous, and a different definition?
Right. So this is interesting. So this is in a selection scenario. What does it mean to be like a good candidate? And I think this is. I don't want to say it's arbitrary, but I think like in practical terms, people who are making selection decisions often have like a limited number of places that they can select people for. And so I think in practice the way it would work is you would like choose, well, I have 100 places, what thresholds would I use to get that 100 places? And then use that to define, and then based on the predictions of who would have GPA scores above the required threshold for that. Does that make sense?
That's one more problem. But this is super interesting, so I just should say that this is actually like a legal argument people have advanced, like this exact slide, which I should definitely talk to you folks about.
Yeah, I'd love to hear more about that.
And it may well be that this is like a legal argument, has its own history that I didn't know about, so thanks.
There will be room. There will be time at the end of the talk for more questions as well.
Cool. So I think at this point, gonna go forward a little. We're going into a group activity. I guess I am introducing the group activity. Cool. So this is to get a little bit of familiarity with what we just said, and also a little bit of a segue to our next session. So we're just going to take a couple minutes, say hi to your neighbors. It would be very tricky to regroup, so I would just say talk to the person next to you. And we have some sort of discussion questions here. So as a corporate recruiter, you have 10 places to offer to 100 applicants using a standardized test. There's a bunch of information you know. 50 are immigrants, 50 are not. You know that immigrants perform slightly better on the job. You know that the correlation of the test score with job performance is low for immigrants and moderate for non-immigrants. And we're going to call a test score above a certain threshold a high test score. In light of this, you can use sort of different thresholds for each group. What do you aim to equalize between the groups? So I'll give you guys a couple minutes to take a look, think through it, talk to your neighbor if you have one, introduce yourself, say hello. Make a buddy for the rest of the conference. All right. Oh. So hopefully you've had some time to think through this. In the interest of time, we're not going to dig too much into it. But for a show of hands, who chose A, equalizing the probability that the job performance is high, given that the test score is high in the group? No, we're also being video recorded, right? So we're like trying to make it interesting for them too. No one chooses A, all right. How about B, the probability that the test score is high given that the job performance is high in the group? A small set of people chose B, maybe 4 or 5 people, okay. C, the probability that the test score is high given the group, divided by the probability that the job performance is high given the group. Oh, a larger number of people. Very cool. And then D, the probability that the test score is high given the group. No one. Cool. So does anyone want to speak to why they chose C?
So yeah, just because of second bullet, it says immigrants are slightly better than non-immigrants, so it would make sense to me to just hire a little bit more immigrants than none, but that's about it.
Yeah, that's a good answer. Is there any other sort of thoughts different than that? Oh, Ben, here or?
So I guess this is just comparison within the group on both sides. So job performance within the group and then test score within the group, which, I don't know, I guess puts people maybe in a more contextual comparison.
Cool. Oh, and one more from Krishnar.
To me, it seems that if the recruiter knew all these 4 facts, then the right thing to do might be to go back and revisit the test score instead of relying on this imperfect data. Otherwise, it looks like no matter what the recruiter does, it's going to affect someone or other. Maybe even if we use differential thresholds, it could be the case that the test amongst the immigrants, the test scores are not a good proxy for job performance. So what if we end up selecting less those who are going to perform less? So we may be preferring, we may be doing disparate impact even within the immigrants, for instance.
Yeah, that's a great point. So what we're seeing here in this sort of diversity of answers is prioritization around different kinds of values. So by prioritizing the second bullet point, you're paying more attention to what you know from history, your prior information about the job. By paying attention to, for example, going back and editing the test itself, you're valuing or paying more attention to the validity of the test itself. And these will lead to fundamentally different outcomes depending on what you want to prioritize. Oh. What'd you do? Oh. Yay. Okay. Cool. And so from there, we'll start moving on to a new phase of ML fairness research, or rather fairness research, that starts to take these things into account.
Right, so we saw in the 60s and 70s, there were all these competing definitions of fairness, and people knew these definitions were incompatible. So I'm now going to cover how people went about deciding between them. And what we see in the historical literature on fairness in testing is that we must look beyond just the statistical considerations and consider the social values and the policies which we want the test to embody. And we see this also echoed in contemporary research in machine learning with talk of social context and goal and values. There was a great tutorial here last year at FatStar 2018 about how fairness definitions relate to these normative values. And I think it's important to remember that quantitative definitions of fairness are means and not ends. And I love this line from Green and Hugh saying we need to avoid mistaking the map for the territory. So the question I'll look at now is, in the 60s and 70s, how did researchers in test fairness think about how these quantitative definitions related to values and to ethical theories? And of the various theories of ethics, the one that is closest, maybe inherent in machine learning, is that of utilitarianism. And Gross and Su discussed this in 1975. They argue that every definition of fairness has either implicitly or explicitly a set of human values or a utility function. And so their recommendation is that institutions should make this explicit. They should make the utility function published. And then they should choose a procedure to optimize the utility function that they've chosen. So the first question adopt the utility function is a question of values, and the second question is then the more technical problem of how do you optimize for that. And for them, unfairness results when an individual's utility function or value system differs from that of the institution, but at least they can observe this explicitly. Note that forcing utilities to be explicit may involve answering some potentially tough questions about what it is that we value. For example, do we value the well-being of prisoners less than the well-being of non-prisoners? So it seems that in prison there are higher rates of violence, sexual assault, and suicide than outside prison. Should we take these into account in a utility function trying to measure the impacts of incarceration? However, utilitarianism is of course not the only ethical lens through which to view fairness. In this paper by Hunter and Schmidt in 1976, they look at 3 different ethical positions around fairness. The first of which they call unqualified individualism. And so their idea here is that the ethical thing to do is make the most accurate prediction that you can, that it would be ethically wrong to leave out a signal if it resulted in a worse quality prediction, even if that signal is a category such as race or gender. And so this relates to some of the quantitative definitions that we saw already, specifically Kirkpatrick, who used race explicitly as a variable in his regression in order to improve the accuracy of predictions. And in 1970, Phyllis Wallace wrote that in some cases, a failure to treat 2 races separately would lead to discrimination. Phyllis Wallace was actually the first woman of any race to get a PhD in economics at Yale. In machine learning, we see this idea in decoupled classifiers and derived predictors, which make explicit use of the race variable A. The second position that Hunter and Schmidt introduce is what they call qualified individualism. Under this position, they say you still have an ethical obligation to try and make accurate predictions, but now they say under this position, you should not treat groups differently. Specifically, you should not use race or gender under any circumstances when making a decision. And I actually think a lot of the debate, a lot of the fairness definitions in machine learning, as well as in test fairness, are actually an attempt to reconcile these qualified and unqualified versions of individualism. Because if the protective variable A is statistically independent, then the question of whether to use A or not actually becomes moot. But of course, the question then is what should A be independent of? And that's where we get a variety of independence conditions falling out. So the third position that Hunter and Schmidt talk about is what they call quotas. And this is maybe best introduced with an example. So suppose that 11% of the population is black. Under this quota interpretation of fairness, you might say the fair representation in Congress, maybe that 11% of members of Congress are black. And as we saw earlier, the ideas of kind of Thorndike, as well as other researchers such as Jones, make use of this idea. Sometimes this approach has been called race norming, which is another word for basically only comparing scores within a group rather than across groups. And as mentioned before, Cotter has a related definition, as well as demographic parity, of course. So another way of applying ethics and values to these quantitative definitions involves zooming back a little bit to think about the context in which decisions are being made. And Jones in '73 asked the question of what if the same group of people is being consistently deprived in one selection situation after another? Does that change our ethical obligations? And Green and Hu make a related point that we need to better understand the bias and unfairness in society and how that relates to fairness in machine learning. So Darlington in 1978, this is the same Darlington who had the graph for those four definitions of fairness. He discusses three different theories of fairness. The first he calls the mechanical view, which is that fairness is purely statistical and no value judgments are needed. He calls idiosyncratic the theory that fairness is value-based, and that there's no point in trying to reconcile different values, that values are incomparable. And the third theory he presents, which is the one that he advocates for, is that fairness both is value-based, but also that values can somehow be quantified. And this allows us to kind of average or interpolate positions between values to reach certain positions of compromise. So, we've covered the 60s and 70s. I'm now going to move forward into the 80s when we see a waning of this research into test fairness. But it's useful, again, I think, to look at the historical context here. So in 78, the US Supreme Court ruled against the use of quotas in education. Of course, Reagan was in the 80s, and his choice to head the Equal Employment Opportunity Commission was Clarence Thomas, who was a critic of affirmative action. And then in 1991, the Civil Rights Act of that year outlawed race norming, which, remember, was kind of only comparing scores within a group rather than across groups. And actually, one of my American friends hadn't heard of the Civil Rights Act of 1991. I didn't have time to cover it, but you can spot the differences. So Nancy Cole, who in 1973 proposed equality of opportunity as a fairness criterion, had this to say decades later in 2001. She said the spurt of research on fairness that began in the late 60s was ultimately disappointing. She said that research had not supplied any analyses to unequivocally indicate fairness or unfairness. And she said, to make matters worse, the views of fairness of the measurement profession and those of the general public are often at odds. And I've briefly mentioned some of the legal stuff that was going on at the time. And I think that it's important that we try and take some lessons away from what happened in testing and apply them to machine learning. And we go into this more in the paper. But 4 high-level lessons that we drew were the importance of staying relevant to the law, the importance of staying relevant to public opinion, relevance to human values, and also relevance to real-world decision-making scenarios. So I've talked a bit already about how the quantitative definitions relate to human values. I don't have time to go into the others. There's probably more qualified people here who can talk about some of these topics. But I do want to zoom out a bit on that last point and consider real-world decision-making and how predictions relate to decisions. And so going back to the 60s again, this is the data that Cleary was looking at in the late 60s. Remember, she was trying to predict GPA from SAT scores for the purpose of college admissions. And I think one question we can ask is, why do we think that maximizing GPA scores is something that as a society we think should be the basis for deciding college admissions? And it may be that we decide that is the right thing to optimize for. It may be that it's not, but I think we need to be very clear about that distinction and why we're doing that. And I think this becomes even more important when we look at this data from 1968. This is from the book that I mentioned earlier by Kirkpatrick. So he's looking at fair employment. And the important thing here is the right-hand side. These are the variables he's trying to predict from the test scores. He's trying to predict whether someone will be fired, what their merit rating will be, and what their job grade and pay will be. And I think these are only good target variables. Well, there's lots of things behind this. But I think trying to predict these maybe assumes that these measures are themselves unbiased. It may be that there's workplace environments which are leading to discrimination in merit ratings, in termination, and in pay. And so if we're just trying to use these predictors on the left-hand side to predict these target variables, all we're doing is replicating, possibly, historical discrimination. So we see this concern with target variables discussed explicitly in the literature as well in the 1960s and 70s. Guillon talks about the need to pay more attention to the effect of cultural deprivation on job performance. Thorndike emphasizes the importance of a relevant, reliable, and unbiased measure of competence. And Darlington asks the question of what the target variable really is. And I see some of the contemporary research like echoing this as well in various ways about the importance of target variables and what they mean. And so the point here is really that what we are trying to predict is a different question of what we should do with those predictions. The predictions are a form of justified belief, but even knowing what something is doesn't imply what we should do. That questions about is and ought are actually different types of questions. One is a question of epistemology or knowledge, one is a question of ethics. And again, statistics is different from fairness.
So there was a lot that we dug into. What we've talked about is just a small slice of it. I'm going to pull out another highlight, which is some of the research opportunities that we saw as we went through the literature. This is also in hopes that some of you might work on this. I'm trying to convince Ben to, but he has like more important things to do. So here's some of the ideas that came out of this. So there's a general difference in emphasis. Testing looked at regression, whereas ML fairness has, until very recently, largely kind of been grounded in classification. Testing work looked at the fairness of scores. Machine learning fairness tends to look more at the fairness of decisions. And in the testing literature, there was originally a framing of unfairness. So they were trying to figure out what the unfairness was. Whereas in machine learning, there's been more of a focus on framing on fairness. Sorry, lots of Fs. But there's enough here that we can kind of see how some of the lessons from previously can now influence us today. So one of the key research opportunities is this idea of unfairness. So Cleary in the 60s, Guillon in the 60s, basically a lot of the researchers in the 60s were looking at this problem of unfair discrimination. An unfair bias. This changed, there was sort of a transition in the 70s with Thorndike, where it became more of a framing of fairness, but also the work became more distinct, more disjunct from the public opinion. So like when you go to court, you tend to go to court because you think something is unfair, rather than because you think something is fair. And so thinking about things in terms of unfairness, what are different kinds of unfairness, how can you actually highlight different sources of unfairness is a clear area for further research that was largely sort of abandoned after the 60s. One opportunity here that follows in the literature is differential item functioning. So we found that into the 80s, as the fairness work sort of took a nosedive, what became more and more common was this idea of differential item functioning, which takes a look at the impact of different kinds of inputs on unfairness. So this is still used today. So in the SAT, for example, if there's an item that you see a significantly sort of different distribution on for different subgroups, it ends up being removed. So this idea of focusing in on specifically the items that are causing unfairness is something that we haven't seen a parallel today in machine learning fairness. Another research opportunity is thinking more about correlations. So the framing of Darlington put everything in terms of correlations, and that helped really connect a lot of ideas together. It would be useful today to also think about fairness in terms of correlations. This requires less assumptions. It's descriptive and observable in the data. It can be used to represent a lot of other fairness criteria, such as those based on confusion matrix metrics, as well as real valued scores. Another research opportunity is figuring out what to do with weak signals. So this is a problem that they worked on in the 60s and 70s that there's been sort of no research on recently. When input features are only weakly informative, how should that change how we think about the model? And relatedly, what to do with low accuracy models. So this came up in the group discussion or the group activity. When models have low accuracy, how does this change how we think about fair decision making? How do we take the low accuracy of the model into account? Another research opportunity that's kind of fun that we sort of realized just playing with this is this idea of converse criteria. So Cleary in the 60s was saying sort of intuitively, is this plot of R and Y higher for one group? We can take the converse of Cleary, basically swapping around Y and R, and say, is the plot of Y and R higher for one group? And we call this consistent measurement error. Similarly, for calibration, we can take a converse calibration just by swapping around the Y and the R, and we'll call this calibrated measurement. To our knowledge, neither of these has really been looked at, but are relatively straightforward. This is a little bit more on calibrated measurement. So it's a little bit unclear, though, what you do if you're conditioning on Y for calibration. Right. Some other research opportunities are around fairness and social choices, and it's really cool to see a lot of work on that here at this conference this year. So how do we fairly resolve differences in values? What does this imply for quantitative fairness? Thinking about things like fair division, compromise, and value-sensitive design. And this is a bit of a summary, so explaining and reducing unfairness as opposed to fairness, changing the framing, taking a look at differential item functioning, thinking about regression and ways to measure fairness with regression, criteria based on calibration, or what's this point that was supposed to make criteria based on? I'm not sure. Yeah, it's okay. Taking a look at correlations, thinking about fairness when signals are weak or when the accuracy of the model is low, better incorporating continuous cultural attributes, and thinking about the role of automated prediction in human decision-making systems, like judges. There's even more in the paper. Tomorrow we have a talk that'll also focus on some complementary aspects as well. Cool, so now, you want to finish it off, or?
You do the slide.
Okay, so some of the takeaways here. So the history of fairness has not repeated itself, but it has rhymed. Quantitative definitions are means, not an ends. This is something that's very clear from the literature previously and is now being sort of rediscovered again. It's critical to make explicit the values and beliefs inherent in quantitative definitions. That will help you choose amongst different kinds of fairness criteria. Fairness criteria won't tell you which one of them to choose. Predictions are not decisions, so it's important to think about what the target variable is really telling us. And there's lots of research opportunities just sort of looking through this literature, looking through the paper. It's kind of like explodes into all different kinds of directions. Yeah. So I think that you should,
So as well as thinking Shira Mitchell, who's been amazing and insightful throughout this, there are a couple other people I did want to thank, because during the course of this project, I realized that some of these historical researchers from the 60s and 70s were still alive. And I tracked down and spoke with a couple of them. One of whom was Marshall Jones. He was once called the most dangerous man in American academic life because of his role in the civil rights movement in the 1960s. He now lives in Florida with his wife Beverly, who is equally, in some ways, even more amazing than he is. She was a really important figure in the women's liberation movement. And so, Marshall helped me understand a lot the context behind this work in the 60s and 70s, as did Richard Darlington, provided some very useful insights. Finally, we'd like to dedicate this to two people, Charles Thomas, who both did work on fairness and also founded the Association of Black Psychologists, which called for the moratoriums on standardized tests, and was unfortunately murdered. And also Tian Cleary, who was really the pioneer of the work in test fairness from a work in the mid-60s. Thank you.
So you mentioned staying relevant to the law. One thing it seems that's emerging is that the law may have been written without full understanding of these ideas, and in some cases may even be sort of self-contradictory. So I'm curious if that same sort of problem emerged in the 60s and 70s, and if the law responded at that time at all.
I mean, that's a great question, and I must admit, like, neither of us know much about the law. I think. I knew nothing about testing before this research, let alone the specific intersection of testing, law, and quantitative stuff, but I think it's a great question.
It's interesting to note that a lot of the researchers in the 60s were very aware of the sort of social activism at the time, and that it was influenced by, related to law. It came out of the Civil Rights Act, which was law. But in terms of like immediate back and forth between people working on fairness and legal scholars, I don't know that there was much there, which might have been part of why it sort of lost touch.
Sorry, just very quickly, just picking up on this point. It seems like the work actually predates like disparate impact as a doctrine, which is right. Do you have any idea if like the work influenced the legal thinking? Because like you could imagine the opposite direction, but it's very possible that it influenced some of the legal arguments.
You would be exactly the person I would ask.
So this paper by Philip Ash in 1966, specifically on the kind of implications of the Civil Rights Act, I think is the closest thing I've read that kind of gets at this question of what influenced that thinking, but yeah.
Any other questions? Oh, yes.
So you point out that ethics is about decisions and actions as opposed to just predictions, right? Can you make any comments on the existing connections between fairness in general or ethics and areas in machine learning where people actually are concerned about making decisions, are concerned about actions like causality, reinforcement learning, and so on? What could those areas maybe bring to the table in this discussion?
So this is an area of machine learning that, I guess I'm not sure how to answer the question. Yeah.
I guess my point is that not all machine learning questions are about just predicting without concern about what will be done. There's a lot of work on causality where you are trying to predict the outcome of interventions.
Yeah,
right?
I see
which is
saying,
clearly something you want to do in ethics, right?
Right.
Likewise, in reinforcement learning, you have a sequence of interventions and you are definitely making predictions about that. So the question was if there is any comment or there is anything you could say about potential relationships between those areas of machine learning and how they could contribute to understand the ethical component as opposed to the
Yeah, so like, for example, I see what you're saying now, but we've seen more work on causality and counterfactual fairness in this sort of fair ML space, but to your point, there's a lot of work on causality which could, for example, directly relate to uncovering unfairness. So there are sort of, reinforcement learning, you can imagine, like trying out different kinds of fairness scenarios and seeing which one leads to some greater good. So I think that there's probably a lot of plugins if you wanted to focus on it. I was kind of thinking we're asking something else, which is like what are some related areas in ethics, like privacy. So this also kind of comes into account when you're thinking about things like subgroups. So how to deal with potentially uniquely identifying individuals by something that might be sensitive like race, that immediately could use a lot from something like privacy to figure out the right ways to do that as well. So I guess it goes both ways.
Thank you. So you mentioned that the research in the 70s, it sort of ended with a bit of a disconnect between the general public and what these measures were really doing. And when I think about it, it sort of makes sense that a person from a general public would not have access to these group statistics or group measures that were really are working towards, whether there is equality, disparate impact between the two groups, and so on and so forth. But a general public would maybe think about, are the decisions made for me fair or unfair? Perhaps sort of in the Dwork's way of thinking about whether similar people are receiving similar outcomes. So I see that even now, also with the measures that you had shown, that we're still going in the direction of these sort of group statistics, equality of these statistics. So do you have any directions on how to move closer towards what a person feels is fair or unfair?
Yeah, I'll just say a couple of things. So actually one of the slides I deleted talked more about the popular opinions question. And this was discussed in some more, I think it was the same paper by Nancy Cole in 2001, where she talks about why test fairness kind of was ultimately unsuccessful. And the point she makes is that individuals, I mean, it often gets reported in the media, these kind of group statistics, 20% admission rate here, 30% there. And the public does tend to latch onto these group level statistics without a lot of context, maybe. So without understanding some of these conditional relationships, just these kind of like, how many from this group, how many from that group, and decisions based on that. The paper by Robert Guillon in 1966, his idea of fairness is that he says people with equal probability of success on the job should have equal probability of being selected for the job. And I think this maps really closely to this kind of individual fairness idea. But yeah, we didn't have time to cover it today.
Hi, Nate Guglin from Airbnb. Thank you for the talk, really fascinating. I'm curious what you've seen in terms of practical translation. For example, in the industrial setting, in a platform operating at scale, it's very difficult to just even know the labels for the protected classes across millions, hundreds of millions of users. And it's also challenging to incorporate fairness prediction and then mitigation into a product launch lifecycle. So in terms of bringing all of these ideas into technology, what have you seen happening in that area?
That's a great question. This has been our lives for like the past 2 or so years, I suppose. Yeah, I mean, the reality is that, you can think about fairness in terms of these protected attributes and things like that, but in something like industry, you actually, don't tend to have those kinds of labels. One thing that we've realized is that a lot of times when people say they want gender or something that corresponds to a protected attribute, they actually mean they want something else, but they're saying a proxy. So, for example, a use case that I've heard for detecting gender is, say you have a customer coming into a store and you want to know like whether to direct them to makeup or not. But what you'd actually want in that case is like people who wear makeup and people don't. And so in a lot of cases, the sort of basic subgroups that we talk about don't apply as directly as something based more on behavior. So that's one thing that's sort of useful in the industrial setting, thinking more about groups of behavior as opposed to the groups of the protected attributes. And then, yeah, like in some cases, it's just impossible, like race. It was interesting to see, the 60s and 70s talk so freely about race, although some people noticed that race is really difficult to define. I think people today are even more aware of that we have some basic sense of like perceived race and how that might create discrimination, but actual race, like self-identified race, is a combination of cultural experiences and national origin and all these other kinds of things. It's defined differently in different countries. And so that becomes really tricky. And so again, you look for things that are more closely related to your task at hand. So for example, if you're working with images, you might want something like Fitzpatrick's skin type as opposed to race in order to look at how the camera is reacting differently. I think that's probably a good answer that doesn't...
Yeah, I was saying.
Yeah.
So I think there's been some interesting work as well on the you don't have access to the attribute. I think there's been some research trying to explore using signals you do have as proxies at training time. So maybe you have access to location, for example, which may be known to correlate with other features. And there's some evidence that if you can make your model fair for location, then you do get some levels of fairness for race, which you don't have direct access to. Right. There was a nice paper by some of our colleagues at AIES just a couple of days ago looking at some of these kind of like practical problems in building fairness into systems. And there are like so many like practical issues that come up to like, the stability of the model training. And, if you're releasing incremental versions of a model over time, like how do you think of fairness longitudinally? Do you care about model stability over time? There's all sorts of like fascinating issues that come up. And one of the things they found actually, which they mentioned in their paper, was, so I found it interesting because they actually use correlation. They proposed the use of correlation as they actually incorporate a correlation term into their loss function. So they're trying to train a model both to achieve the desired outcome, but also to minimize these correlations. And what they really wanted to do, they told me, is like, use independence instead, because like every statistician says independence is the correct thing to do. But I think there's like and we know that independence is a different thing from correlation, but I think it's an interesting question of like, even though in theory there's this important difference, like in practice, often correlation may be a very quick and useful signal in practical scenarios.
I'm going to ask a quick question since I have control of the mic. So I really love this whole sort of meta paradigm of like looking to history to guide sort of how we're thinking about things currently, and I think it's really nicely highlights the fact that a lot of the sort of problems within this sphere are not new, and they are just sort of new versions of existing problems that come with sort of scale and automation and all of these things. So I'm wondering if in the course of this research you have any insight into other areas within the kind of general sort of ethics, fairness sphere, apart from sort of fairness in decision making and testing systems like this. Do you have suggestions for other areas that people should look at to try and understand historical patterns and trends apart from this particular one?
Yeah, so this is kind of a general thing I like to do, but I don't know if you're baiting me to answer this, like how I'm going to answer this. So another area where this has really come to the fore is in computer vision, where there has been recent work within the past 2 years of people trying to predict like criminality, for example, or things like pedophilia, these other things. It turns out that the basic approach, which is analyzing the face based on an image in order to figure out some sort of future state or some internal inherent characteristic, has a history going back as far as I could find. I think 5,000 BCE was when I was stopping, but basically as long as humans have written about other humans, they've tried to use our faces to predict behavioral things, and it's given birth to racism in a lot of different forms. And so there's a piece that I worked on called Physiognomy's New Clothes. It's on Medium, which basically makes the point that physiognomy, the science, the sort of pseudoscience of trying to say whether someone is criminal or not based on the face, is something that is common to humans, that deep learning is another way of doing the same thing, still picking up on the same sort of superficial characteristics under the guise of scientific measurement. And so to answer your question, yes, I think it's just generally important. Computer vision is one area. I'm sure there's a lot more in language processing as well. It's sort of like, because humans have been humans for a long time, we tend to have very similar ideas throughout time, so it's always really useful to take a look, yeah.
We have time for at least one more question.
this is just a really fast add-on to your question, which is to say that, speaking as a historian, there are lots of historians out there who have been working on the history of statistics, psychology, testing, education, et cetera, which is just to say, go and find them and talk to them, because they, so I think this work is amazing, and it really articulates the need for interdisciplinary and cross-disciplinary collaborations. I mean, it's awesome that you have done this historical work, but there are lots and lots of folks we could all be drawing on.
I saw a hand up here. Yeah.
Hi, just two really quick ones. Firstly, thanks a lot. It was really interesting and really useful. Great having the context of the work being done and the context in the US. For anyone, I'm from out of the country, from another country, and but on the weekend I went to the National Centre for Civil and Human Rights in Atlanta, which is amazing. And it really, if anyone from out of Atlanta hasn't been there, I encourage them to go. It's free this week, sponsored by Coca-Cola apparently. But you can go along there for free. It's only about 20 minutes walk from here, and it provides all the context so you understand much more about what you're talking about. Now, the second the question is, I assume that the literature you've talked about is all US literature within that US context. Has there been much international literature on this, for example, from Europe or anywhere else that any of those have referred to, or that takes a different trajectory?
That's a great question. I'm also not from America. And as I did this research, a lot of this just history stuff was new to me before making all these connections. So it's something I feel. So yes, I continue to get sidetracked. I was trying to stay focused on this particular story. I would love. Emma said I did a terrible job of staying focused, perhaps, but I would love to see more cross-cultural and international work on fairness generally, both in the current context, but also understanding better what has happened historically around the world. I'm sadly not familiar with that, but I would love to meet and talk with historians who know more about this.
We basically found that for any little thing we looked into further, there was tons of other information. And so part of my job working with Ben was to say, no, stop, no, go back. So we didn't explore the economics fairness stuff, which goes back before 1900. And we didn't explore outside of the US, but I'm sure there's a lot of other stuff. Yeah.
Yeah. Hi. I just wanted to ask if, sort of related to this whole thing of gender being a proxy, for example, for another thing you want to measure. Is there any good research on avoiding feedback loops and self-fulfilling prophecies? Because if you market a product exclusively to women, more women will buy it, and then gender becomes a better proxy of the thing you're trying to predict over time. So how do you avoid that, or sort of?
I mean, that's a great question, and it also pops up in recommendation systems a lot.
Oh no, go. I just had another thought.
But I'm not actually familiar with that research, and you know more than I do.
Oh, I was just going to say that I think there's a paper here that looks at this a bit. It's polarization. Looking at how different groups can become polarized. So I think there's recent research that's starting to look into it and the problem of feedback loops. We didn't see a lot at the time, and I think in part that's because today we're dealing with deployment of the same system on a massive scale in a way where I think feedback loops are a lot easier and quicker to notice and measure, whereas before it was, there was one test you might take and it'd be a subset of people. So the feedback loop problem is definitely a more pressing problem now. And yeah, hopefully there will be more work on it, but we didn't come across stuff from the previous work.
Okay, so I think we're out of time, so I'd encourage anybody else to come talk to our speakers offline. And just one more plug for reading their paper. It's going to be presented tomorrow in the main conference. It's called 50 Years of Unfairness. It's a really just phenomenal piece of work. So yeah, let's thank Margaret Mitchell and Ben Hutchinson again.